here you see the correct deformation of the contour, which helps you to find the correct asymptotics of our solution, and the corresponding deformation of the lower branch cut, which allowed us to actually deform the contour in such a way. So quite a peculiar thing. And naturally, the lower deformation is not a deformation at all. It's actually coincides with the initial placement of the contour and the branch cut. And of course, the asymptotic is found by the vicinity of the lower branch point, and it stays the same. It's the same incident wave. The second asymptotic, the second contribution, comes from the vicinity of the second, in this case, now it's upper branch point, minus 2 IKS. And let's not bother for a second about the lower asymptotics. It essentially stays the same. Rather, we concentrate on the computation of the second asymptotics. And probably you already guessed that it's not that difficult, because there are basically two contributions. One from the lower bank of the branch cut, and the symmetrical one from the upper bank of the branch cut. You just need to take special care about of the arguments of the corresponding t variable. And indeed, we have this here multivariate function. Let's call it g of t. And of course, it should be defined in a single valued manner, so we should fix the regular branch. And the way we fix it, we just impose the following condition. If t is large and positive, then g of t is of course reduced to t to mu minus 2, and we choose the regular branch in such a way that this asymptotic is positive. Right. So now let's actually track down the change of the arguments of our both of these factors when we circle around this upper branch point, minus 2 IKS. Well, first of all, let's track the change of the argument of the t to mu minus 1. So the delta argument of t, well, as you probably see, so initially it was Так, Андрей, сейчас я маркер уронил. Сейчас, секунду. Так, это надо будет увидеть. Initially, the direction point in pi direction, and then it rotates clockwise by pi by 2. So in the vicinity of this point, argument of t has, it's changed, of course, by minus pi by 2. And the argument of t itself is pi by 2. Now the argument of t plus 2IKS. Right. So now it points in. So yeah, it points in this direction. When we glide along the lower bank of the branch cut, it points in this direction. So it's kind of, it's actually, it's either minus pi or pi, so we should actually define it. Well, it used to be, I think it's minus pi, right? Because it used to be, it would be minus pi when when the point was positioned here, and then when we slide upward, it's the same minus pi. And when we are above the branch cut, it's minus pi plus 2 pi. It makes the full rotation and slides again to the minus infinity. Now we have an idea how to compute the contribution for the second branch point. So we just expand again these two functions. Now t is equal to parameterized as minus 2IKS plus rho to e to minus I pi below, and plus I pi above the branch cut. And we just plug in this decomposition into our exact solution. So now T becomes that kind of thing. And the convergence of the integral is defined by the vicinity, small vicinity of this branch code. So rho is less or of the order of 1. So in this expression for T, when we plug it in here, we can discard actually the second term, the term proportional to rho, comparing to the first one, which is large for large s, for s much greater than 1 over k. So in the end, what we get is as follows. So I just skip the details because they are trivial. It's just a simple algebra. And for your phi function, you get the following expression. So you can check it yourself. And of course, this basically represents you the expected behavior of the wave function, because the wave function is obtained by the multiplication as to sorry. Okay. Oh, sorry. Of course, it should be S2 minus mu. S2 mu times e to I ks. And now you have the combination of the scattering wave, because the first term after the multiplication will become, so the incident wave, sorry, and plus the scattered wave. And keep in mind, so this is the pre-exponential factor, which comes precisely from this peculiar deformation of the contour. And it represents the scattered wave. And as we see, it's proportional to the sign of pi mu, and mu is the factor which was related to our initial potential, namely mu squared minus mu was equal to kappa squared a squared, where kappa was 2m, kappa squared was 2m u naught. So what we see already from here is that the scattered wave disappears if mu is equal to some integer number. And via this relation, it imposes the specific values of the potential depth of the potential well. And in this case, we already see the famous phenomena. The potential becomes reflectionless for some particular values of potential independent of the initial of the energy of the incident particle. Right, now let's figure out how to compute the actual reflection coefficient. To this end, we need to compute the corresponding semi-classical expressions and match them with the solution of this exact Schrödinger equation near this the turning point, or in our case, the pole of the potential. So the semi-classical expressions are as follows. You just compute the integral p dx from the turning point to some x. And let me redraw the picture for you. So here is the complex plane of x. Here is the position of our pole of the potential. And here are two proximate turning points. And at this point, we'll call it x naught plus, and this is called x naught minus. They're close to each other. And we define our semi-classical integral as going from x naught plus from this point. It's a matter of choice. Of course, you could choose x naught minus. It doesn't make any difference. So we choose x naught plus to some distant value of x. So we rewrite this integral in terms of our s variable, because s is simply x minus x1. And as a result, we get the following. So it's kappa squared minus, oh sorry, k squared minus kappa squared a squared over s squared ds. And s stretches from kappa a over k times some large values. It is an elementary integral, and its antiderivative is very simple to compute. So I'll just give you the answer for large positive values of s. And the answer is as follows. It just, so s much greater than 1 over k. And you easily obtain ks minus pi over 2 kappa a. And now, when you look at the structure of our reflected wave or incident wave, what we immediately can do, we can substitute this exact exponents with our semi-classical expressions, which are true for in the regions of the complex plane of S, which are much greater than the concrete vicinity of the pole of our potential. Right. So once we do the substitution, we obtain the following semi-classical equation, which is basically one of the last steps in our solution. So it's c over square root of k. Naturally, square root of pi is changed into square root of k for large values of s. And for the incident wave, we just get e to I p dx from x naught plus to x. And for the reflected wave, for positive x. And for the reflected wave, we have this combination, but we just substitute ks factors with their semi-classical expression. All right, so what we get is just e to p dx plus 2I sine of pi mu times e to minus I p dx, and minus this phase. In fact, it is doubled. The phase here is doubled because we factor out, when we plug in this decomposition, we already factor out e to minus pi by 2 kappa a. And now we have the doubling of this phase. But it's, of course, irrelevant for the computation of their scattering reflection coefficient, which is in store on our next slide.